just practicing for the SVD, singular value decomposition stuff that's going to come. You know, just pretty great. So the self high five. Okay, so right. The goodness that is about to happen is positive definite matrices, right? So this is a little excursion again into some another area of linear algebra that's very useful. We will use a basic result from it when we get to the singular value decomposition, which is the promised land. And but this is going to be useful in other ways. Okay, so all right, so let's just start with this. There are a couple of definitions. We'll get to a different definition soon, but there are a couple of things here, right? So positive definite matrices. Okay, so these are hilariously matrices that are very sure about themselves. Okay, so real symmetric matrices, and so this can be expanded always. We don't talk about complex numbers in this course, but everything can be expanded. But we're going to start with real symmetric matrices, so therefore n by n, square matrices still. And this is the big deal, right? So that they have positive eigenvalues. So every eigenvalue is greater than 0, right? So we have n eigenvalues, they're all greater than 0. Now, that's going to have some uses, as we'll see. There are a number of little results here, so I'm going to have 3 pages here on just talking about how you find them. Okay, so that's important, right? So this is just a start. This is how we've defined them. I'm not telling you why they're useful yet, but the game first will be how to find them and understand them, just analytically, and then some examples of their usage. You'll see for some reason there's a saddle over here, right? So there's going to be a couple of pages on that. Then we'll have this rather remarkable thing that Gaussian elimination and completing the square. Good old completing square, very similar things. And that will connect again. And this idea of principal axis theorem, right? So it's about, let's say, ellipses, ellipsoids, hyperellipsoids, trying to orient your axes so that everything is correct. And all of these will have positive definite matrices underneath them for some reason. All right. So there's an extra piece here. We just say that we'll have semi-positive definite. We'll call matrix semi-positive definite very nicely if at least one eigenvalue is equal to 0, or we believe that to be true, right? Okay. So if this is the only condition if this condition is relaxed a little bit, we had greater than 0, then we just say semi-positive. All right, fine. We can talk about negative, definite, etc. That's fine, but this is a framing. We use a Pollyanna approach. So we orient in the positive. All right. Right, just like language. We don't say unsad for happy. We say happy, sad, and unhappy also means something. And we'll even say not unhappy, but that doesn't mean happy. But we usually define negatives in terms of positive. Such biased creatures we are. So, okay, so we know 2 things about real symmetric matrices for a start. This has been this wonderful result. So they always have 2 pieces. So the first is that the eigenvalues are real, right? Have real eigenvalues, which makes them simple, so no rotations. Again, complex numbers sort of a little bit beyond what we're doing here, but that's what that means. So this means flipping, stretching, and shrinking, right? That's the sort of things that those eigenvalues do. A times V equals lambda V. If lambda is greater than 1, it means you expand in that direction. If it's less than -1, you expand, but you flip as well, etc. Stretching, and that is not what I was going to put strengthening, shrinking. Physical training. All right. This and a complete, right, a basis for Rn, right? So they have a full, let's write it like this, eigenvectors that form a basis for, I've missed out the very important bit, form and we can make them all an orthonormal basis for Rn. Right, so this is pretty cool. So this is the whole, right, so this is A equals Q lambda Q transpose. Which, right, you ordered that hat, right? The hat that has this factorization on it. Yeah. Should be coming with the X-ray specs, right? So yeah, $10 includes shipping. Okay, so it turns out that that if we add this, right? I'm reading my own thing. So we've got this for real symmetric matrices. If we add this next piece, that the eigenvalues are either strictly greater than 0 or greater than or equal to 0, then these turn out to be matrices that we find in the real world, and we also make things into them. Right? We'll rearrange problems so that we get PDMs, positive definite matrices, because they have these great properties. So there are going to be two things to work on here. So there's going to be one, so how to spot a PDM. So there's quite a bit to this, but I'm going to keep it fairly simple, and it's rather surprising actually, right? So why we like them, that's sort of in the whole, these next episodes. But how to spot a PDM. So this is surprising results from monks, right? Always with the monks. Very odd. So we're going to connect pivots and eigenvalues. Pivots and eigenvalues. They come from very different parts of linear algebra, if you like, very different problems. But they will have a connection. Right? We're talking about eigenvalues here, but pivots are easier to get to. That's the point. Pivots are easier to get to. So if we can find out something about pivots, then we'll be in good shape. All right. So more things about what we're going to see. So this equation, which turns out to be an equation of ellipse, matrices, right? So we're going to connect it to matrices. It doesn't look like a matrix problem, but we're going to do that. You know what? I'm going to clean that up. We usually have this kind of, right? We've elevated things a little bit here. So this should be really just x1 squared. I want to keep that. x2 squared. Yep. Okay, good. So somehow that's connected to matrices. Right, we're going to have this, what elimination really does, if for symmetric matrices, right? And completing a square will be involved. So you've surely done that many times, completing a square. And will we have this? I think I'll delete that. All right, so we won't have that. Good, bye-bye. All right. More things will come. Okay, so we're going to work with these matrices. So normally, right, you would compute the eigenvalues. Fine, right? We compute them. So let's just sort of take that as, computing happens elsewhere. You figure it out. You can verify these things I'm going to tell you. So we have 3 and 1, and I'll put in that the plus 1 plus 3. Over here it's root 5 minus root 5. And all that's happening is there's a change here, there's a minus sign here, and then a new minus sign here as well. So that's the difference as we go across. So we just change them a little bit. Of course, these are potentially big changes for matrices, just flipping signs. Might look a little easy to us. Minus 1, minus 3. So what we have is, this is a PDM. PDM, right? So that's if you want to use an emoticon, you may. We'll use this antique one. Not a PDM. So that's sadness. Again, taking this point of view that we want them, right? Nope. Okay, so because of this, and here we have 2 negatives. So the one on the right, you know, you just flip it upside down and it's, but we're going to, again, positives, right? All right. So the problem is, okay, fine. So this is the game. We find the we have a real symmetric matrix. We find the eigenvalues. So here is the problem, right, that blunts our happiness, is finding eigenvalues can be hard. You know, can be pretty hard, right? So that's okay. It's usually easy if you do numerical work, which is a course you could follow up this one with. Then you see that finding the largest one and then maybe the next one, that's not so hard. But finding all of them can be pretty hard. You know, for real matrices, real life matrices that you just find on the street. So we only want to know the signs, right? We only want to know the signs of the eigenvalues. You know, the Ace of Base song is actually about mathematics. Surprising. We want to know signs of the eigenvalues, right? We only need that. So could there be a sneaky way? Right, one that helps us, helps computers, right? Sneaky way. One, you know, one that's so especially one that helps computers, right? Because ultimately we want to get computers to do things. Again, ultimately they'll make us do things if they keep us around. But in the interim, that's the plan. All right. Okay, so here is a surprising thing that I don't think you should have expected, right? Again, monk-based madness. What have these people been doing? Okay. So, sneaky monk trick number 37. So we've got A is symmetric. It's n by n. It's real, meaning real entries. Then it turns out that this is true. So let's give this a nice big color. So the number of positive pivots, this is very strange. The number of positive pivots is equal to the number of positive eigenvalues. And the number of negative eigenvalues is equal to the number of negative pivots. And the number of zero pivots is equal to the number of zero eigenvalues. That's really odd. It's just an odd thing. We knew before that the determinant of A, and I'm sure that's what you're thinking, right? The determinant of A, we already know the determinant of A is equal to the product of the eigenvalues and plus or minus the product of the pivots. So we'll have that again just here. So we know that. So we know that products are related up to a sign, potentially. But this is a more detailed, weird thing, right? So we've highlighted in the Pierce Hawthorne terminology here. Crazy Town Banana Pants. And you should watch Community, great show. And so this is a very peculiar result, right? So it is very odd. So the eigenvalues and pivots come from very different parts of matrixology. Linear algebra is apparently we ridiculously call it. So they do, right? One is from the AX equals B problem, like solving that, and then AV equals lambda V. These are just different problems. So we already have this piece, as I've said. That's a connection between them. But there's this larger piece, right? The sneaky trick number 37, right? That says that the signs match up. And then we have this big deal down here that so if a right, this piece, so if a matrix is a PDM, positive definite matrix, then if all the pivots are greater than 0, then, it is a positive definite matrix if all the eigenvalues are greater than 0, and we can now say that's true if all the pivots are greater than 0. And the big deal is that the big deal is that the pivots are much easier to compute. All right, so that is our plan. We're off, right? So let's try to understand why this is true. I'll give you a 2x2, and hopefully you can kind of see how this will generalize. Right, we have to do some more math to prove it all. Let's take this second A2. It had these eigenvalues plus or minus root 5. Again, you could figure that out if you want. You can pause and work that out. So what we're going to do is see how the signs of this one match up to the signs of these eigenvalues, match up to the signs of the pivot. Okay, so we're going to do LU decomposition, the thing we've always done, right? So we would take, right, so we're going to subtract minus 1/2 of the first row from the second row, which is a bit of an odd thing to do. It means that we're going to add half of the first row to the second one. But this is our L21, right? So the way we've always structured it, right? So we use, if you like, row 2 prime equals row 2 minus 1/2 times row 1. Right? So this is our L21 in here. This is L, and this is U. Right? So in general, we get this structure. Now, because A2 is symmetric, right? So A2 equals its transpose, right? A2 equals A2 transpose. We like to make that clear in any factorization we do, like Q lambda Q transpose. It's very clear. And something that we did at the end of LU is we'll do LD L transpose. All right, so that's all of this stuff. We've still got L here, minus 1/2, 1. This just has to be true. We're going to pull out the pivots, right? So here's pivot 1, here's pivot 2. And if we do that, minus 5/2, then we'll get an upper triangular piece here that is, in fact, the transpose of L. All right. So this is a nice thing. Okay, so now we're going to work with this. We're going to play with this form of A2. Right? A2 is, sure, it's back here. It's 2 minus 1 minus 1 minus 2, but we're just going to forget about that for a while. And we're going to work on this form. Right? This is going to be an easier thing to kind of follow the behavior of. And we'll actually go after this parameterized matrix here, B, and we'll make L21 a function, a variable. All right? So it looks exactly the same, but we've just put in L21 here and L21 here. Okay? So maybe I'll get rid of some of this stuff and connect these things. So, right, good. And naturally, when this variable is minus 1/2, then we have B of this B matrix as a function of minus 1/2 is A2. Now, okay, so what we're going to do is we're going to move across. We're going to shift it across this B thing. We're going to change this matrix. We're going to dial L21 to 0. Right? We're going to tune this to 0. Right? That's what this question is here. So what happens is we move from L21 equals minus 1/2 to 0. Right? Let's think about that. So let's just talk about it here. We're going to have an identity matrix here, right? This will be 0. And we'll have an identity matrix here. So as we tune L21 to 0, we end up with this matrix B is going to be just D. Good. Right? So let's see that here. It's exactly what this is. Identity, D, identity. Right? So this B matrix, and you can see this was sort of generalized, right? If we want to do this for all sorts of other matrices. So And in fact, because it's a diagonal matrix, we don't have to, if we want to find the eigenvalues or the pivots, they're just sitting there. Both of them are sitting there. So for diagonal matrices, the pivots and the eigenvalues are the same. Maybe I should add that as a statement. Right? So for diagonal matrices, the pivots are exactly equal to the eigenvalues, right? We don't do any row reduction, we don't have to solve any, it's all sitting there. Okay, so what do we have? We have these pivots, right? Again, this is D1, this is D2, so they're listed here, D1 and D2. Now, all right, and in fact, okay, so these pivots don't change, right? So here's the thing. As you vary these two pieces, we're going through a whole bunch of, right, we've got a parameterized set of matrices, so we're going to tune this. The pivots are sitting here, they don't change, right? We've got different L and L transpose, but this is a matrix with the same pivot. All right, good, good. So for all L21, same pivots, right? The determinant of all of those matrices doesn't change, right? So this is independent of L21. The determinant is equal to -5, and again, that's independent, right? It's just the product of the product of these two pivots. Okay, so we also know, so there's a couple, so there's these big connections follow here, right? So big connections. We also know that the determinant is equal to the product of the eigenvalues. And we started with √5 and minus √5. So let's put that in here. So this is √5 and minus √5 for L21 equals -1/2, right, for A2. So this must be -5 for all L21, because the determinant doesn't change. Okay, so that means that the determinant is never 0, for example. So as we're tuning this around, the determinant stays stuck. So that means that none of the eigenvalues can hit 0. This is the big idea. None of the eigenvalues can hit 0 because they can change, but their product has to remain -5. And if one of them went to 0, then obviously the determinant hits 0. And that's the only way for the sign of an eigenvalue to change as we dial this L21, right? Okay. The 2-1 multiplier. As we dial that around, we can move it all over the place. When it's 0, we have this very simple matrix, just the diagonal matrix with D1 and D2, 2 and -5/2. When it's -1/2, we have A2. We can dial it, you know, from -infinity to infinity. We'll just dial it around. The determinant never changes, and therefore the eigenvalues can never change sign. So this is what, you know, all of this is. So if you want to read through this, right, it says the eigenvalues cannot change through it. This is our statement from before, and I guess I have it. Yep. The pivots and the eigenvalues match up, right? So when the multiplier is 0, which means they have exactly the same signs, right? So that means as we move away, if we move away from 0 to -1/2, the pivots don't change, but the eigenvalues go to plus or minus √5, and that means that they had to have been a plus eigenvalue and a positive number and a negative number when it was 0, right? Okay. All of this is to say, and if there's a pivot that's 0, we just tweak the matrix a little bit and move it away from 0. So you can do all these things. All of this is to say that we just need to find the pivots and take their signs, and then we know that these will be the signs of the eigenvalues. Pretty awesome. Okay, there's a picture of what happened here. Again, just to sort of try and cement this idea. So we're going to go from between -1/2 and 0 for our multiplier. When it's -1/2, we have A2, When it's 0, we have the diagonal matrix, right? Just this thing here. And these are the balances on each side, right? So we're going to have, for the A2 matrix, we have these eigenvalues. For the pivots, we have 2 and minus 5 over 2. They do not change, right? These are invariant. Invariant. And these change, but signs remain the same. Pretty cool. Okay, so in fact, you can generalize this. So this is A, it's an n by n, and it's got to be symmetric. It's got to be real. Those things are all true. And then we have this piece. We could say, all right, let's think of a different L. It's going to look like the L we had, but we're going to have the identity plus T L minus I. So when T is 0, this is gone, and we just have the identity. I should write this as, I guess I should write, yeah. Yep, we have the identity. The matrix we're creating is, right? And then when it's 1, we have L, the underlying L. Yeah, so what I want to do here really is say we'd have a B, we could call it B of T. T equals L, this thing of T, D, L transpose, and this is a function of T as well. So B of 0 would equal D, and B, right, these are just the identity, and B of 1 would equal A, right? So this is as before, right? Pretty good. So the pivots won't change as we move this T around. The eigenvalues can't change sign, and so therefore the signs of the eigenvalues match the signs of the pivot. So the upshot is this, right? A is a positive definite matrix if all of its pivots are greater than 0. This is the piece to take away. Right? You should understand the whole proof, but this is the thing to take away, and also that we're interested in these positive definite matrices. All right, so that's good. The next thing will be just seeing a very nice example of how to use, or where positive definite matrices are quite naturally used. All right, carry on.